Hi, and welcome back to MSc. In today's lesson, we're going to be looking at chemical equilibria, but specifically looking at calculating equilibrium concentrations when we have a very small Kc value, when that equilibrium constant is very small. So here's an example. An equilibrium constant for the chemical reaction below here is 2.0 times 10 to the negative 6 at 350 Kelvin. Determine the equilibrium concentrations of all substances if 6 moles of substance A was placed in a 2-liter vessel and the reaction was allowed to reach equilibrium, again at that same constant temperature. The temperatures here don't matter for our calculation, but they do affect the Kc value, so it's important that this number matches the number up here, right? But it's not something we're going to use in the calculation, but remember from Le Chatelier's principle that temperature does affect the Kc value. So we are going to set up a nice chart for this, and we're going to look at our initial concentrations. Now, this question was a little bit differently worded. Don't forget, concentration is mole per volume, and the concentration of A initially was the moles were 6 and the volume was 2. So that means I have 3 moles per decimeter cubed here as my initial value. I have none of this initially in this question. But watch for that. The other examples that I've done, if you haven't watched those videos, go and check them out. But they each had a 1-liter vessel. So they were a little bit easier there, so just watch for this. I know I'm going to lose some of A. I'm going to say minus X. B is going to gain X because it's a 1-to-1 ratio. But then C is going to gain 2X. So my equilibrium amounts will be 3 minus X, X, and 2X. Okay? Now, if we tried to solve this, without this approximation, things would get a little bit more challenging. But because we have a small Kc value, we can make an assumption. We can assume that this value here is approximately just equal to 3. And we can make that assumption because Kc is small. And when we say small, it's a bit of a arbitrary value, but we're saying Kc is less than 10 to the negative 3 is usually a good rule of thumb. And so here we have Kc being 2 times 10 to the negative 6. So here Kc, as the previous slide said, it was 2.0 times 10 to the negative 6. So this is definitely a small Kc value. And we're going to assume that it doesn't go to products very much, and that once we round, we would just get our 3 back. So this assumption here can make our calculations a little bit easier. We're going to have to calculate our K expression. And so we'll say the K here, Kc, is the products raised to their coefficients. So it's squared on the C, all over A raised to its coefficient, which is just 1. Now we can sub in. So we'll say B is just X, C is 2X, and that's squared. A, instead of putting 3 minus X, which would lead to a messy equation to try to solve, we can just say it's 3, and that's how we sub in this approximation. And again, this is equal to Kc. You can sub this value in for Kc, but I think it's actually just as easy to write Kc. This is maybe not the nicest number in the world in terms of having to write it down repeatedly. I'll just carry Kc through this for a little while, but feel free to sub that in right away if you'd like. We're going to rearrange here and bring 3 across. So 3 Kc is equal to, and let's do some math here. So this is X times, and this is squared. So this is 4X squared. X times X squared is X cubed. So I'm going to have 3 Kc is equal to 4X cubed. Let's get rid of this 4 on both sides. We'll divide by 4, which will cancel it on this side, which is great. And what we're left with here is 3 Kc over 4 is equal to X cubed. Now, in order to solve for X here, we're going to have to take the cube root of both sides. And in doing so, I'm going to move my x onto the left side by convention here. I'm going to say that it's equal to the cube root of this expression. 3 times kc all over 4. And this is where I would naturally then substitute in. I'm a big one for not substituting until it's fully rearranged. So that's why I've done this here. 2.0 times 10 to the negative 6 all over 4. And that, again, is what x is equal to. So when we calculate this, we get, which is just now a calculator problem, we get 0.011447 ... And this thing's going to continue on for a bit. So that's our x value. We won't round that quite yet. But we have to remember that, again, this is not what we were asked to do in completion. We were actually asked to find these equilibrium concentrations. So let's go and try to do that. Let's look at the equilibrium concentration for B to start with. And the B equilibrium concentration was just x. So this is 0.0114, but to 2 sig figs, this would be 0.011 moles per decimeter cubed. Concentration of C at equilibrium is going to be 2x equals 2 times 0.0114 ... which will give us 0.02289 ... which rounded to 2 sig figs would just be this, 0.023 moles per decimeter cubed. Now let's look at the concentration of A. We assume that it didn't change, but we know that it should be 3 minus whatever that x value was. And that x value is a slight approximation because of what we approximated a bit originally, that it stayed at 3. But let's double check to see how good of our approximation was. So this is 3 minus 0.0114 ... And when we do that calculation, we get 2.9885. And then we would, and that would continue on. And then when we round as 2 sig figs, this would actually round back to 3.0. And so this means that our approximation that we did originally seems reasonable. We got an x value, we checked it here, and so that looks like our Kc approximation was good. So these small Kc values can lead to an approximation that can make your math a lot easier. We didn't have to solve a cubic function with this. We just had to take the cube root. And that was something that we were able to do in this example. I hope this short example has been helpful. Thank you very much for listening. And as always, thank you very much for watching.